Hello, everyone. My name is Fadi, and I thank you very much for joining our webinar today on 2D DIC and material testing. Today's topic is a topic that we addressed before, but since it's very important and we have lots of interest in this topic, we decided to give you this new webinar on the power of 2D digital image correlation and how powerful it is for material testing applications. Before we start, the technical content of this webinar, I would like to give a very brief introduction about ourselves. We are a material testing lab in Greenville, South Carolina, focused on advanced material component testing. And we distinguish ourselves by focusing on a few points. The first one is the use of state-of-the-art facilities and sensors. In particular, our emphasis on the use of digital image correlation and optical metrology sensors. And we tend to use DIC with almost all the tests that we perform. We also focus on the skills of our personnel. All the people who work with us are technical people with a good background in material deformation and understanding of material deformation and failure. And finally, we try to elevate the outcomes of conventional testing and try to stretch the limits with specialized and customized testing and analysis so that we can address complicated testing scenarios. I typically like to cover one aspect of the test that we perform because we do a wide variety of tests, as you can see on the screen, between tension, compression, formability, fracture, and even some component testing, as you can see here. So to do that in a nice way, I usually pick a video to play and demonstrate one of those items that we focus on. And today I picked an old video. This is a video for a high strain rate test that was performed about 3 years ago on a third generation advanced high strength steel. It is about a gigapascal in terms of strength and more than 50% in terms of ductility. And the reason I picked this old video, relatively old video, is because it's a very unique test, but at the same time, it was performed with 2D DIC, which is the topic of our discussion today. So I thought this is just a nice start to show that this topic of 2D DIC is not really new. We've been doing it for years, but we feel like there's more emphasis today and more interest today in 2D DIC, and that's why it's nice to address some of the technical aspects related to 2D DIC and how we can achieve it. Just a very quick snapshot of the people that we work with, different R&D departments in different sectors, particularly the automotive sector, but also some other sectors. So let's go back to the webinar. And again, the title of our webinar today is, yes, 2D DIC is still powerful and effective for many material testing applications. To start, or to give you an overview of what we are going to cover today, we will start with a very general introduction about DIC in general. Then we will focus on the problem statement for today, which is the perceived limitations of 2D DIC and the issues that some people see with 2D DIC and the argument against it. And we will address those argument points one by one in a technical discussion with some information, sometimes analysis, but then we will keep the majority of that discussion to the experimental section, in which we performed concurrent experiments in which we use 2D and 3D DIC together so that we can provide technical quantitative comparison between the two systems and thus answer the big question, how good is 2D DIC and is it really accurate? And finally, we will conclude with some remarks. So let's start with a very, very brief introduction about DIC, because I feel like after 2 or 3 years doing these webinars, we feel like most people are now familiar with the concept of DIC, and it's not really a new concept anymore. But just a quick reminder, we use this simple schematic to describe what DIC is based on a tension test. And this is just a general image of a tension test equipped with a commercial standard 3D DIC system with 2 cameras, monitoring basically a tension sample during a standard tension test. And so to describe digital image correlation, the idea is to take images of the sample or the material that is deforming. And from that image, we basically divide the area of interest, which is the deformation zone, in this image into small regions. Each region is a certain number of pixels in the X and Y, and we call this a subset or a facet. We take each one of those subsets or facets and we focus on them from one image to the subsequent image throughout the deformation, and we try to track the center of this facet as it is moving in 3D space and also as it is deforming, whether it's stretching or contracting. And by doing that, for each particular region of interest, now we have information about where this point is moving in 3D space as the sequence of images is going through. And by gathering all this information for all those points, we now have a full deformation vector field that can be converted to other engineering quantities. Of most interest to us in material testing, of course, is strain. And so you can convert this vector field into strains by basically taking the delta L over L. And then ultimately you get a nice strain map as the one that you can see on the right-hand side, where the different colors indicate higher or different levels of deformation in the material. An image that usually mimics what we are used to seeing from finite element simulations. So that is basically the basics, or these are the basics of digital image correlation. On a tension test, if you take, for example, this schematic for a tension test, the starting image is there, and then somewhere down the road in the test, right before failure or somewhere before failure, we took another image there. So the whole idea is to take those facets, and I just basically identified this zone here of interest as a facet, and tracking this particular zone later in the test. And as you can see, a square subset or a facet becomes, in this case, for example, rectangular, and that basically gives us a sense of how we get the positive longitudinal strains and the negative transverse strains in a test like a tension test. And then ultimately, as I mentioned earlier, we take this for all the points in the material deformation domain, and we get these nice strain maps. A typical DIC usually generates nice videos, which we usually like to show to demonstrate how we can monitor the deformation of the material during the test, and even also correlate it with certain events in the test, typically portrayed on a stress strain curve. Like in this case, you can see what the material is doing in the elastic region, in the hardening region, and also most importantly, for many investigators, they are interested in the material during the necking or the fracture, right before fracture. So in many webinars before and in many applications, we've shown how DIC truly transforms the way that we characterize material deformation and failure. It gives us information well beyond typical sensors. Of course, we need forces and we need displacements to construct the stress strain curves, but DIC gives us more and more. And that's why we tend to try to push for digital image correlation. However, let's dig into the problems and the limitations. Before we go to the 2D DIC problem, let's talk about the limitations and the hurdles that 3D DIC faces. So even before we go to the special case of 2D, when we talk about digital image correlation in general, there are some limitations to why we don't see them used as extensive as we would like to. The main limitation for 3D DIC systems is the fact that those systems commercially available are relatively expensive. Generally speaking, they're considered expensive, especially for R&D centers, research, academia, and so on. And the second problem is the fact that even those 3D DIC systems are sometimes used for very simple tests, like the tension test that you can see on the right-hand side. They're not really used extensively for much more complex applications where they should be used. And finally, there is an argument out there that the stress strain curves, if you talk about the tension test, can be constructed without a DIC, and that's absolutely true. You can construct the same stress strain curve with the same accuracy from a typical extensometer. So why bother with this expensive technology that we call DIC? The answer to that is, of course, dependent on different opinions. We believe that regardless what, DIC still is powerful, transforms the way that we characterize material deformation and failure. It gives us insights, information that is beyond just curves. And we believe that so many people would like to access DIC and they would like to integrate it into their material testing applications or component testing applications. And now is the time to do it because resources, we believe, are now more available to enable people to do that. And from that perspective, we feel like, one good approach to do that, especially if we cannot overcome the main hurdle of 3D DIC and its price, is to go with 2D DIC. So why not start using 2D DIC? And that's where we take the focus to the 2D DIC system or basically application. 2D DIC is basically the use of a single camera instead of two cameras. You don't have depth information with a single camera, unlike 3D DIC, and therefore it is inherently coming with a major hurdle, and that is the limitation of its applicability to in-plane deformation only. So that is one major restriction for 2D DIC, is that most people say, okay, I can only do planar tests, so how good is it, or is it really worth it, and so on. But then the second problem, which is the major problem, the more important problem, is that there seems to be a pushback in the community against 2D DIC. There are different labels that 2D DIC gets, and some of them are maybe inaccurate, it's inadequate, involves a lot of error, it's harder to deal with in terms of calibration and so on. So between these two hurdles, we feel like there is a push against 2D DIC, and that's why we don't see it out there. So we wanted to approach this problem and ask a specific technical question here. And this technical question is, how good is 2D DIC? How accurate is it? How repeatable is it? And maybe a second part of the question is, how good are measurements made with 2D DIC systems compared to 3D DIC systems? If we were to assume that the ideal case scenario is to have 3D and that those measurements are perfect, how does 2D DIC compare to that? And that takes us to this webinar today. We would like to achieve our goal of promoting the use of 2D DIC, even if it's a start into the DIC world. We believe that there's so much that can be done with it without compromising quality. We can still get fantastic results with 2D DIC. And to prove this, this webinar tries to address the technical issues and also provide experimental validation by doing a direct comparative study between 2D and 3D DIC to show how much is the error involved and how repeatable, reliable 2D DIC is, so that it gives people comfort, people who are interested in this direction, to give them more comfort that maybe some of those labels against 2D DIC are not truly correct. So let's go to the technical part of this webinar. Before we go to the experiments, we decided to review what we have seen or heard in the literature, in technical conferences, workshops, and so on, some of the argument against 2D DIC. And here I'm summarizing the 5 main points that we've been hearing. The ease of setup, the calibration or scaling problem, the out-of-plane error in general, and we will discuss the details here, lens distortion or barrel distortion, and finally, these direct comparisons between 2D DIC and 3D DIC on a point strain level. So let's take them one by one. The first one is, there is some argument out there that 2D DIC can be described as much harder to set up than 3D DIC. And the particulars of this argument is that once a 3D DIC system is calibrated and everything is set, then you can literally not worry about the configuration of the system, and you can just move it back and forth, no problem, so long your sample is within the field of view or the measurement volume, as we call it, then you should be fine. You can tilt the cameras, you can skew to the right or to the left without worrying about any of those effects, and that is true. But part of the argument says that 2D DIC must be perfectly perpendicular to the deformation surface, and if you cannot achieve that, then it's a nightmare, you're not going to get good results, and so on. So we agree with some of those arguments about the 3D DIC and the fact that once it's set up, it's really good to go and you don't have to worry about it. But we don't agree with the fact that 2D DIC is harder just because of this. In fact, 2D DIC as a setup is much easier to set up because it's simply a camera that is in front of a sample. You don't really need to do much after that. In fact, in terms of setup, there are so many scenarios where 2D DIC is even easier to set up because of accessibility problems. So putting one camera in front of the object is easier than putting two cameras with a certain distance and spacing and so on. In terms of calibration and scaling, it doesn't require calibration, which is an extra step in 3D DIC that could be problematic. So it just requires scaling. And that scaling does not have to be really super critical, as we will demonstrate later on. And finally, in regards to the point that 2D DIC must be 100% perpendicular to the sample, we have a lot of information about this later today to show that it's not really that, that sensitive to the point that, you would spend like, half a day in making sure that the setup is absolutely perfect. So let's go to another point here, which is the calibration or scaling. So 2D DIC scaling is often described actually as inaccurate. People say that, yeah, it doesn't work, or it's not really good enough. It's not like the 3D calibration or the full calibration in a 3D DIC system. Some comments out there is that scaling, of course, is necessary to establish the connection between, the image and actual physical measurements. But the fact that it's performed typically in a manual fashion without calibration panels brings a lot of inaccuracies. And any error in the scaling could lead to inaccurate displacements and results. While some of this is true, in many material testing applications, what we care about is strain, and this must be remembered. What matters is strain, it's not displacement. And so it's a game of relatives. And if you understand the error that's associated with that, you can kind of get a sense of how sensitive is your measurement in 2D DIC to all these parameters that are related to scaling. And to demonstrate that, we will talk about how we do our scaling and what kind of results we get with it to try to address some of these issues. Because ultimately, like I said, strain is a delta L over L. So even if you have inaccuracy in the scaling, how much does that translate into with regards to the amount of error that is in your measurement? And finally, nobody said that you couldn't technically calibrate or scale accurately with 2D DIC. You can still do it. And you can use a calibration panel, or you can use a good scale. What we are saying, or what we have seen in our experience, is it doesn't really have to be done super accurately. But if you want to do it, it can be done. And that eliminates a lot more of those errors if need to be. The bigger or the biggest technical argument against 2D DIC is out-of-plane error. And of course, 2D DIC is only good, generally speaking, so long that the camera is perpendicular to the surface, and that is a true statement. Anytime you go out of the plane of deformation, you're introducing errors because the cameras cannot capture depth information. This error that is associated with off-perpendicularity is there. The question is, how big is it? And there seems to be like an exaggeration of the amount of error that comes from this off-perpendicularity. And that's usually driven by two attributes or two cases. One of them is referred to as the movement or the change in distance between a camera and a deformation surface. And what that means is, let's say you set up a 2D DIC system in front of a test sample, and somehow after you did the scaling, you moved the camera 2 millimeters closer to the sample or away from it. Somehow you bump the camera or something like that. So this will cause error, an error that you don't have to worry about in 3D DIC. Some other argument with this is vibrations in the testing machine, or thinning, buckling, bulging in the test sample. So we will try to address this in the next slide. But before that, let's talk about the second type of out-of-plane error, which is what we call tilting error. And this is, simply speaking, that when you set up your DIC camera, it wasn't 100% perpendicular to the sample. So what does that mean in terms of error? So let's discuss these two errors because they are very important, and we're going to try to go a little bit more analytical. So the first error, which is the change in distance, this is a schematic to show what we're talking about. Again, you scaled your DIC for a certain reference distance, which is, let's say, M0, and then somehow you bumped the camera and you moved it closer to the sample, and now the distance is M. So, okay, what is the measurement error? But luckily, you can do this simple analysis quite easily. by triangulation. And we did this, and you can kind of get a sense of the amount of error that is involved here if you're trying to measure nominal strains. And what we found out is, even for a decent movement of 5-6 millimeters, your error should be, theoretically speaking, and this is just a calculation, within the 1%. So it might not be that significant, especially if you're trying to measure strains in a tension test. And that these measurements, or sorry, those calculations shown here, they were intentionally done on a setup that mimics the most popular tension test, which is the one per ISO 6892. That's same as ASTM E8 or the comparable German or Japanese standards, the most popular test out there. We still don't see a significant error from basically calculation perspective. One special case of this scenario is thinning. Now, thinning during a tension test happens. It's very critical, important. And when it happens, that implies, even if your camera hasn't changed or moved, that your sample is deforming, necking, and so that part of the deformation zone is going further away from the camera by, let's say, whatever, quarter, half a millimeter. So what are the implications of that on local strains? The argument that we see out there is like, okay, it's out of plane deformation, so it's done deal. These strains are bad, wrong, you cannot use 2D DIC. So I don't have an analytical way to convince people otherwise. So we will wait till we get to the experimental section to try to provide evidence to how this issue is not really as big as it's sometimes portrayed. It is there, of course, we are not denying it, but we feel like it can be addressed with the proper approaches, and the experimental study that we're showing here today will try to hopefully give some numbers to prove that. Let's go to tilting. And this is a schematic of a perfect setup, ideal setup. Camera is perfectly perpendicular to the object. So tilting means if it is not perfect and you move the camera at some angle with respect to the surface, you will introduce error because there will be a difference between any length or change of length that's perceived by the camera compared to what actually happens, because it's going to be a projection. And these schematics, again, can be simply constructed. And we constructed two scenarios. If you're looking down, or basically from a bottom up, or if you're looking from a top down. And both cases are valid, and they generate kind of different types of errors. One of them produces a perception that's higher than actual, and one produces a perception of a length change that is lower. But regardless what, the analysis can be done, and you can tabulate and you can plot it. And that's what we're showing here on this slide here, is that you can estimate theoretically the error that's associated with such a computation. And we found out that within 5, 6 degrees, 7 degrees tilting, the error is still within 1%. You can even go to about 8% theoretically speaking, and your error would be within still 1%. And so that's an indication that maybe these errors are not that large. And again, we're not encouraging people to set up the DIC without paying attention to this. What we're saying is you don't really have to make it 100% perfect, and a couple of degrees off perpendicularity might not be that bad. But again, we will try to show evidence from experimental data. Next item is lens edge distortion, or what we call it barrel distortion. And this is an issue not with 2D DIC. This is a lens issue. In any lens, depending on the quality of the lens and the relationship between the lens and the sensor of the camera, you will have this distortion. It's shown in this schematic here. And that is when you're monitoring a flat object, like a flat panel. In reality, if you grid it into a square grid or a rectangular grid, what you're going to get as this image is taken to the sensor of the camera through the lens, this grid is distorted, especially around the edges of the field of view, and that's caused by this lens barrel distortion. This distortion cannot be completely eliminated per se from a manufacturing perspective or from a lens perspective, and it is there whether it's 2D or 3D DIC. However, in 3D DIC systems, it's not that critical of an issue because we have the calibration. So that takes care of it, or most of it, in a 3D DIC system, so you don't have to worry about it that much. In 2D DIC systems, of course, there is no calibration. So what do we do with it? It can be addressed. what we say is this point is absolutely valid. However, the distortion is not that significant if the proper optics are used with that type of camera that you're using. So with the proper camera selection, lens selection for a camera, and with understanding of this problem, you could offset a lot of this error, and we will show how we address this in the results that we obtained in our experimentation. Last point here is point strains. This is something we see a lot. When people try to show how bad 2D DIC is, you typically see something like this. And I don't have actually data to show from other presentations. So what I did is I took a tension sample, and this is something that close to what you would see out there. They would show, like, for example, a deforming object and maybe a point here or a point there, and they would show like the amount of strain at this point based on 2D DIC and then based on 3D DIC. And typically the error or the deviation shown is extremely high. I saw recently a deviation of about whatever, something like this, 25 for one case to about 30 to 40% in the 3D DIC. So it's a massive error. So that's a proof that 2D DIC is not good. Our opinion is that, honestly, this is all irrelevant. We don't believe in any of these point comparisons, because point strain is absolutely meaningless in material testing. It doesn't mean anything. It's not really a physical quantity to look at. All what it means is you're taking basically a local strain measurement at a point which has no relevance whatsoever in practical applications, because what we care about is relative displacements and strains between points, such as an extensometer or over area average. And this issue is so critical, and we try to discourage people from even going down this route with point strains, because even if you have a 3D DIC file, fully calibrated with a good calibration, and you click on any point from your software to get information about the point strain there, we still believe that this is completely inaccurate, because you still have hot spots in 3D DIC measurements, and those point strains are not reliable at all, even in 3D DIC. So the true comparison should be based on strains that are relevant to us in mechanical engineering properties, evaluation or extraction. That is typically an extensometer. So the proper question should be, in a tension test like this, if I identify 2 points, let's say they're 50 millimeters apart, how does my 2D DIC measurement compare to the 3D DIC measurement? That's what matters, and that's what we are going to try to focus on in the next session. So to sum up here, before we go to the experiments, there are so many points raised against 2D DIC. They are good points. They deserve attention. They should be addressed. They shouldn't be ignored. By no means we encourage people to dismiss them. No, but what we're saying is they shouldn't be accepted as is, without quantification and without experimentation or explanation. And we've noticed that most of these arguments against 2D DIC could be qualitative and not really quantitative. So we decided, why not perform an experimental study and put these arguments to the test and provide some real quantitative answers. And that leads us to the experimental section here, or experimental part of our study. We performed a wide range of experiments with 2 systems, a 3D DIC system, commercial, very capable 3D DIC system with 12 megapixel cameras, with a good setup, good calibration, and so on. And then we put one of our 2D DIC systems. We even tried actually several 2D DIC systems, one of them matching the camera resolution, so 12 megapixel camera with the same kind of parameters, but we also considered other cameras like 2 megapixel, 5 megapixel cameras. So we even intentionally tried to drop the resolution of our 2D DIC to see, does it really affect the results that much, and does it really lead to those errors that are portrayed as 10, 20, 30% sometimes in the literature. We use the same exact software in the study that we're showing today, although we have used some different software sometimes to show that even if you use different software, softwares, it shouldn't make a significant difference. In fact, in our presentation in April, we did try to show results from a couple of softwares, and they showed very good match. But for today, we're going to focus on the same software. And our approach is very similar. We took several testing cases between the simple tension to of different sizes, from sub-sized to normal standard size to very large size, kind of a sample like the one I showed in my previous picture. We did tension, we did compression, shear, plane strain, and so on, different varieties of tests so that we can test 2D DIC. We considered many materials between aluminum and steel alloys with different strength and ductility levels. And we considered different parameters. Sometimes we kept the parameters as close as possible between the 2 and 3D. And sometimes we even varied it to see the sensitivity of that. And we will present some results today. Of course, obviously, we cannot show all the results. So what we decided to do is pick just a couple of highlights important to all of us, especially on the tension testing, fracture testing, and shear testing. But we will make the rest of the data absolutely available to everyone, as we will describe later, so that you can even view the other cases or even the same case for other materials, because we have lots of data that we welcome people to review and see how it compares. So let's take a look at some of the results. And I will start with the ISO 6892 type 1. That's basically an ASTM E8 in North America, the very popular test with a 50 millimeter virtual extensometer. And this is a sample video that was obtained with 2D DIC for one of those tests. And you can see nice stress strain curves, nice strain measurements, and nice DIC mapping. We are seeing correlation all the way to the end of the test. And here's the same test captured with a 3D DIC system. And you can see stress strain curves are smooth again, and the strain maps are correlating quite nicely until the fracture point. So no significant difference between the two. When we try to process, as I mentioned earlier, we process to try to achieve the same reference length. And this doesn't really mean much most of the time, but in case of those people who are using finite element simulations to try to take the data from an experiment to try to do some sort of calibration with a meshing in finite element, what that means is when we did the reference length, we tried to match let's say a finite element mesh, like a 1 millimeter mesh, 2 millimeter mesh, or grid, and so on. We matched the field of view and the reference length. And here are some results that we obtained for a couple of those materials. I start here with an aluminum alloy. This is 187 is a 6000 series aluminum alloy. Nice stress strain curves. You could barely tell the difference between the 2D and the 3D. The curves are on top of each other. The end of the curve, or the ends of these curves, they show disparity between sample and another, not between 2 or 3D DIC. And this variability is just a material variability. When we go to the stress strain curves, which are important to our finite element colleagues, that's what matters. Hardening curves are exactly the same, no difference. Let's go to the mechanical properties for design purposes. This is a table showing all the mechanical properties, and I know I cannot go through it today, but we welcome you to study all these tables that we will provide to show every single mechanical properties. The differences are either negligible or small, very small, and it depends on the quantity. But in this particular case, the results were fantastic. 3 repeats almost on top of each other for almost every single one of those mechanical properties. We go to the DP980, challenging material used a lot in the automotive sector. Limited ductility, so let's see how much is the error here. And again, we see the curves are on top of each other, engineering stress strain curves. The differences between them at the end are technically, again, material repeatability from sample to sample. But even with 3 repeats, here's the true stress strain curves that will go into an LS dyno or an autoform simulation, and it's exactly the same, indistinguishable difference. As we go to the mechanical properties, I picked the DP980 because we knew we're going to get more deviation from this material. But even here, the deviation between 2D and 3D DIC is indistinguishable, or it's very small for the majority of these properties, especially like stresses, uniform or total elongation. It's very close. The N value, the hardening, is exactly the same. The R value is very small. The most we saw in terms of difference in the Young's modulus, and this is a very valid point. We always say 2D DIC has a limitation in the elastic region. It involves more error than 3D DIC. So if your only interest in a tension test is elasticity and you want it super accurate, we advise you to go to either 3D DIC or a high quality extensometer, because 2D DIC will involve more error. But even with that, if you look at the results that we're showing here, the error is within 3%, 4% in the worst case scenario that we saw for 2D versus 3D DIC. Let's go to a more complex tension test. This is a larger tension sample. We call it the UT30, and this is a similar test performed the same way, but these samples are 3 times larger to some extent than the standard test, and they are used because they are a better representation of the material to give us more information about fracture testing to match finite element meshes or grids that are used in crash simulations in the automotive sector. Here's a video of those tests. Again, it's just a slightly larger sample. Well, it is a larger sample, and you have a stress strain curve. I think this is for a DP980 again. You can see correlation all the way to the end. So even in the necking zone, we are getting a correlation all the way to the end, and we can obtain some fracture strains in the localized zone. And here's another video for the same test in 3D DIC. And again, similar level of quality in terms of the correlation of this test. Okay, so let's go dig deeper. Let's look at stress strain curves. And I want to show like 2 extremes. One of the maybe largest mismatches we've seen in this kind of testing. This is for an aluminum alloy, and we see like a tiny deviation between the first and the second approaches, 2D versus 3D DIC. Tiny deviation on the true stress strain curve and the R value. And this is one of the largest we've seen. But when we look at the mechanical properties and the end value that is used for the simulations, the table shows that these deviations are still very small, within a 1% error. We go to another material. This is a mild steel, extreme repeatability. They are on top of each other. And here I would like to stop for 1 second and explain something else we did. Typically, when we did this study to do a comparison between 2D and 3D DIC, we would take the 3D DIC first, and we would identify 2 points for the extensometer, and we would draw the strains from that. Then we would go to the 2D DIC image. We would dig for those same points that define that extensometer and identify them point to point, and we would extract the strain from that. So this is matching the extensometer. And then we did another scenario where we just basically said, no, I don't care where this extensometer is taken to the DIC. Let me take it somewhere else. The same 50 millimeter extensometer, I just want to take it randomly somewhere else in the sample. So that's what we call here arbitrary. Nevertheless, you can see the orange curves and the purple curves are literally on top of the blue curves. So there's no difference whether you match or you don't match. So basically taking 2D DIC measurement as is and doing the natural process of obtaining strains will work and will give you the stress strain curves that you see here. And the same thing with the mechanical properties. Like I said, please feel free to review these tables in more details to see which mechanical properties induce more errors or show more errors or deviations from 2D DIC when it is compared to 3D DIC. Last but not least, very challenging material. We decided to take one of those aluminum alloys, 5000 series aluminum alloys that are known for their PLC banding, and thus you see this very serrated, very rough stress strain curve. But again, when we follow the same approach, 2D versus 3D shows no distinguishable differences between the two. They're on top of each other despite the roughness of the curve. And for those who are not familiar with these kinds of materials, 5000 series aluminiums, when you deform them, they start, basically propagating generating bands that we call PLC bands that propagate across the sample until they lead to localized failure. And again, this is just a replay of the video, and you see how the serrations just basically are reflections of the roughness that you see in the stress strain curves, or vice versa, basically. Again, with the mechanical properties, even for this material, we obtained some really good comparisons. Let's go a little bit deeper, a topic that is of interest to people, fracture testing. This is a very important topic, very critical to so many people, especially research institutions, R&D centers. They want to get more information about fracture strains because they want to calibrate their gizmo cards for crash simulations or any fracture model for crash simulations or so on and so on. And that requires accurate measurements of localized strains. So let's see how bad 2D DIC is. This is a DP980. We're looking at the strain map right before failure. And just to help you read these images, I just summarized them in these tables. The major and minor strains, basically the extensometers, nominal strains are within 1% error. They're almost indistinguishable, no difference. Let's go to the fracture strains, and we have like 1, 2, 3, 4, 5, 6 millimeter fracture strains or extensometers, and we picked a couple of them here, the 1 millimeter and the 4 millimeter virtual extensometers. And for this particular material, we still got results within 1%. And that's fracture strain, localized. They're higher than the deviations in the nominal, and that's expected. But they don't grow to the level that they are on, on an astronomical deviation of 20, 30% or 40%, as it is sometimes portrayed. Can we repeat this? Absolutely. Here's the same material, another sample, and here's the deviation, 1 to 3%. Transverse strains, as we said in a previous webinar, tends to show more deviations than nominal longitudinal strains, but still, you can still get it within a reasonable error. And here's another one for the fracture strains within 4% maximum for one of those virtual extensometers. Now, I want to show you even another extreme. We did this comparison in a previous presentation where we did a very, very, very crude 2D DIC setup. Nevertheless, we got about 1% deviation in the nominal strains because we believe that it's very easy to obtain such match between 2D and 3D DIC. But when we went to the fracture strains, we intentionally messed up the angle of the camera. We made it so high that you can visually see that the camera is not perpendicular to the surface. And nevertheless, the major strain at 1 millimeter extensometer was about 10%. When you convert this to true strains, it's about 7%. And so the question is it really that bad? So the answer is no. Even if you mess up your setup, and we don't encourage you to do that, but what we're saying is, even with a crappy setup to some extent, these strains do not affect the accuracy of your gizmo calibration. And for those people who work with this stuff, finite element crash simulations, and they're really familiar with the process of the calibration, what matters, these strains that you're measuring with DIC do not really reflect a 10% deviation in the calibration parameters for example, a gizmo card. What they mean, or what they represent, is that zone that you can see there, which is the end of the load displacement or the engineering stress strain curves. And what typically happens is that we take these endpoints of the stress strain curve or the load displacement curve, and we use that descending down portion of the curve to obtain certain parameters, like the decaying factor for a fracture model, and so on. And those deviations that you see there between 2D DIC and 3D DIC are actually, in most cases, much smaller than the natural deviations between sample 1 and sample 2 and sample 3 when you do repeated tests on any material. And I'm showing here on the right-hand side an example of one material that was extremely repeatable in terms of mechanical properties. You can see the stress strain curves are on top of each other, but their endpoints are totally different. And that's absolutely normal in material testing because you cannot replicate fracture. So if the error in DIC measurements with 2D DIC is so tiny compared to that, that tells you what kind of error are we talking about. And so it's all a matter of perspective. Of course, if you look at the numbers and someone tells you, oh my God, that's 5% or 10% the difference, you should trash 2D DIC. That's actually not true. That is nowhere near true because the variability in the material testing is way greater when it comes to this critical topic of fracture testing and calibration of, let's say, a gizmo card. And I just put this slide here for those people who are familiar with the process. Is when you obtain this fading exponent and the fracture strain, the tip of the load displacement curve, you know that this is not going to affect that much. How much is the movement in your basically stress triaxiality curve that you obtain from this calibration? Last but not least, I wanted to show just a couple of slides about a very difficult test, which is a very tiny test, localized in nature, involves usually high strains or plastic strains, and that's the shear test. What you see here is a video of a nice shear test that was performed on a DP980, localized strains, and this video was obtained actually with 2D DIC. You can see the curves are nice, obviously, and the deformation zones were captured, correlated nicely all the way until the point of fracture. And when we took the same strain maps at particular, basically locations in the shear test, maybe early on, middle of the way, and then towards the fracture point or close to the fracture point. And we compared the 3D DIC and the 2D DIC. We noticed that the deviations are very small. To help you read these numbers, here are some summary tables. Within 3% deviation between 3D and 2D DIC. Within maybe 3-4%, also 3% here. And close to the point of fracture, the deviation is also within 3%. So, and this was done with a decent setup, very nice setup. And that's why we can obtain really localized strains in shear testing with, we typically say you can get it nicely within 5%. And again, going back to shear testing, you must remember the objective of these tests. It's not a matter of comparing numbers. The numbers don't mean anything if they don't lead to a final conclusion. And the final conclusion of a shear test is typically calibration of a fracture model to obtain a point on the fracture strain versus stress triaxiality curve. And again, we go to these load displacement curves in shear testing, and we see that those differences are just represented by those deviations at the tips of those curves that you see here, which are nothing compared to the material variability curves themselves, regardless of what extensometer you use. So in summary, I know we presented a lot of information. We started with some background information and then with some technical discussions about 2D versus 3D DIC. And then we went to the experimental study. And like I said, we showed just a small portion of those experiments. But the main highlights and the main points that I wanted to mention here at the end of our webinar is that we're trying to show here that 2D DIC is still a very powerful tool. It is a fantastic tool for those who want to use or start using DIC, and we encourage that. And it is still not just a toy for people to start playing with DIC. We believe it's a very good, effective research tool if done properly and if used in the right applications. So you will come across some pushback, and that is okay. And there are points raised, and I mentioned maybe 5 of them, and there might be some more out there. And we welcome any more criticism or feedback from the community out there to tell us if we're missing anything that's really important. But regardless what, these points, we don't deny them. We say that these points are valid. They are important. They deserve attention, must not be ignored. You must take these points into account when you set up or use DIC, but we caution from not using these points as a discouragement or saying, okay, this is an evidence that 2D DIC is not adequate for material testing or it's not good for research and so on. We tried to show this by a discussion, and we did also provide a detailed experimental study that showed clearly that 2D DIC is pretty good and the errors involved are not as large as sometimes perceived. We will make all this data available. The presentation will be made available on our website. Of course, the recording will be made available as well. But even the files, the experimental files, the Excel files, and the DIC strain maps and the DIC videos for all the tests, the ones that we presented today and the ones that we did not present, they will all be available on our website, and we will send an email to all the participants so that you can go ahead and download. In fact, we will even include the raw images from our 2D DIC and the raw files from 3D DIC for people who would like to take these files and play with them themselves. They want to, let's say, play with parameters or change the DIC correlation parameters and evaluate the error for themselves. We definitely encourage that. We wanted to end this webinar by saying we encourage you all to start using DIC, even if it is 2D. There are plenty of applications, even though they're planar. That's not a major restriction. 90% of most of the tests that people do on a daily basis are done on a tension machine. So that kind of tells you that most of your tests are planar in the first place. So what's the problem? Then we have a lot of applications that we can use them. On our new website that we will release in about 2 to 3 weeks, we will provide a specific basically page or a specific tab just focused on 2D DIC. And we will provide nice overview, good technical material, research applications. So we're going to present some academic applications and some general applications, testing applications, and also we're going to try to address the needs of those researchers in academia and R&D centers. We're going to talk about more complex tests than these. We're going to talk about, of course, shear testing, fracture testing, but we'll also talk about compression testing, cyclic testing, and plane strain testing, those localized tests that can be also done with 2D DIC. And we will even provide guidelines for how to set up, what are the parameters, how to select for this particular application, how to select the proper 2D DIC system. We will offer ready-to-go 2D DIC experimental kits that can be used with a wide range of softwares that are available, and we will provide a list of those softwares that are available to you that you can use them for correlation. But we will also encourage you, if you would like to build your own 2D DIC system, you want to match your camera to a lens, to a light, we will definitely support you in that direction too. And being in North America, we welcome, of course, questions from everywhere around the world. But if you happen to be in Germany or in Europe in general, we have our colleagues from MIGO in Germany. It's a nice team of young guys with a lot of experience in DIC, just like us, and they share our passion for spreading 2D DIC, and we encourage you to reach out to them. If you have similar questions or needs for 2D DIC, they have lots of experience. They're doing something similar in terms of pushing for 2D DIC, and they will definitely help you and answer your questions, and even show you data to compare 2D to 3D DIC. With this, I would like to conclude the webinar for today. Thank you so much for attending and for your attention. I would like to thank you again for giving us the time. We hope you found this webinar useful, and we look forward to see you in future webinars. Thank you very much.